As the next step, let's look at Eigen decomposition. So this is a decomposition of a matrix A. So let's say we have a certain matrix of constants, and we'll want to decompose that matrix into a form that makes it easier for us to analyze our differential equations. And towards this, it's useful to think of a matrix as an object that rotates a vector. So if we have a vector y, our original vector y, when we multiply a and y, then we'll get a new vector, and that vector will generally not be in the same direction as y. And just a simple example towards this, let's say we have the matrix A, and it has the constants 1 and 2 above and 3 and 4 below. And let's say we consider a column vector u, which has values 2 and 1. Then the dot product there, it's going to be 1 times 2 plus 2 times 1. And so we get the 4 here. And then for the bottom part, it's going to be 3 times 2 plus 4 times 1. And so we get the bottom part. So we get a column vector 4, 10 like this. And as we change the constants here, we get other vectors. And you can see the numbers will change significantly there. So we are saying that we have some original vector. So in our space, let's imagine we have some starting vector. And after we multiply it, we get some other vector. So perhaps we get a vector like that. Or if we take a different vector, let's say there's a vector here, then we might get a different result altogether. So perhaps we get another vector that lies somewhere here. So this operation of the product of A and a vector gives us a new vector, and that's generally fine. But we are going to propose that there are some special vectors, right? So we have a constant matrix to begin with, and we are multiplying by our choice of vector. And we are going to claim that there might exist a vector such that when we multiply that vector by A, the result that we get will be parallel to the original vector. So once more, we are doing this operation, dot multiplying a matrix and a vector, but we are saying now that there are some special vectors which are such that we can get the result by multiplying by a constant. In other words, the result is parallel to the original vector. So there are certain special vectors where this property holds, and we call those eigenvectors. And you can experiment with this. You can propose a matrix of constants and try out a series of values for y, and you'll find that there are certain vectors where you have the result being parallel to the original vector. And there are some nice videos on YouTube. If you look at the channel 3 Brown, 1 Blue, or videos by Zach Starr, you'll see some nice visuals of that. So let's take as a given for now that there are certain special vectors with this property. So those are vectors which are properties of the matrix A. So associated with the matrix A are special vectors which, when you multiply them with A, you will get a new vector which is parallel to that vector, to that special vector. And so we have this property. And we let lambda be the constant, which, if you like, the parallelizing constant. So what's the number that you have to multiply y by to get the result? So this constant lambda, that's a single value. And for example, if the matrix Y is 2, 1, and lambda is a 3, then 2, 1 times 3 gives us 6, 3. So the result here is 6, 3. So lambda is a certain fixed value. And so that's the eigenvalue that corresponds to these special eigenvectors, right? And so we have these special vectors, and let's call these special vectors V, right? Y is general. Y can be any vector. Let's let V be the special eigenvector. And so we can say that this property of it being parallel, that the Z, we can determine Z from the special constant lambda times the special vector V. And then, of course, that's the Z, and then we still have A times Y. In this case, it's A times V. So this is the special form that we like now. It's the only vectors V can say this. And now we can also say that there might exist more than one such vector. And in fact, it can be shown that there are, generally speaking, for a matrix of rank R, there will be R eigenvectors. So if we have R eigenvectors, we will arrange them in the column space of a new matrix, which we'll call V. And so if we create this matrix of vectors V, so we've arranged them in a matrix now, then we also want to create a matrix for lambda. So we will stick in all the corresponding values for lambda as the diagonal of a new matrix. So this is the symbol for capital lambda. So capital lambda is the matrix with the values lambda written in the diagonal. And that's equal to, and here it's A times, and the vector form, right, V in the column space is here. So that's the vector version of the same equation. And we can say that we can rewrite the matrix capital lambda as the inverse of V multiplied by the right-hand side. So that's the eigen decomposition that we're looking for. And we're going to find that quite useful in our differential equations.